So today we're going to talk about NL a little bit more, non-deterministic log space. Last time we were sort of halfway in the middle of proving, most of the way through proving two theorems about it. First, that it's contained in polynomial time, just like log space, and also that it's contained in deterministic space, log squared n. And as we'll see, it's basically because the computational power of non-deterministic log space is exactly the same as the computational complexity of the path problem. The problem of given a directed graph and two vertices determining if there's a path from one vertex to the other in the graph. So besides being relatively natural, I mean taking log space and adding non-determinism on top of it is somewhat natural. As we'll see, it exactly captures the complexity of this extremely natural problem, finding paths in graphs. So that's another reason to like it. And as we saw last time, this problem of finding looking for paths in a graph is solvable in space log squared n using Savage's algorithm, middle first search. And we also know it's in polynomial time using breadth first search or depth first search. So that's sort of the reason why NL is contained in these two classes. But we'll have to look at things a little bit more carefully to finish the proof. And after that, I want to be able to exactly quantify what I mean by saying that the complexity of NL is exactly the same as the complexity of this path problem by showing that the path problem is complete for the class NL. It's sort of the hardest problem in NL. Every problem in NL reduces to it. But in order to make sense of this, we're going to have to define a new notion of reduction that's more sensible for log space classes. Okay, so that's the plan for today. So let's recap where we were. We were sort of in the middle of talking about these two theorems, why NL is contained in P and in deterministic space log squared n. And the idea was to sort of study the configuration graph of the computation of a non-deterministic Turing machine on an input x. So let's say n is some non-deterministic Turing machine. Let's say it has space complexity log n. And let's say we give it some input x of length n. So then last time we got started talking about this directed graph you can associate with the machine n and the input x. So I wrote it as g. And it depends on n and x. So what are its vertices? Its vertices are the set of all configurations of the machine on the input x. So remember, the configuration is defined by the contents of the work tape and the state that the machine is in, and where the head is pointing, which can be encoded in the string, and also where the pointer is on the read-only input tape, which is a number between 1 and order n. So in fact, 1 and n. So it can be written with log n bits. So as we saw in the previous lecture, and maybe also the lecture before that, the number of all possible configurations is basically 2 to the, or constant to the space bound of the machine. Okay, because this machine uses at most log n space here. This requires log n space. So the whole thing is polynomial in n. So there are polynomially many in n different configurations for a log space bounded machine to be in. And if it was a deterministic computation, then everything happens deterministically. Once you're in a configuration, you know what the next configuration is. What's the next configuration? What is the next configuration? And so forth. But in a non-deterministic Turing machine, it's effectively like there's, let's say, 2, without loss of generality, different paths or branches the machine can take at any step. So it has 2 transition functions, which give rise to 2 kind of next configuration functions. And you can imagine, if you like, that at every step, whenever the Turing machine is in a certain configuration, one branch or one fork goes into one transition and one goes into the next transition. Or sorry, the other transition to the other configuration. And then there's a sort of funny notion of when a non-deterministic Turing machine accepts. It accepts if any of the branches or any of the forks eventually reaches an accepting state. OK, so the picture of this graph is like this. Remember, there's sort of a distinguished start state, which we call maybe C sub start, which looks like Q0, the starting state of the Turing machine, and a blank because the work tape is initially blank. and maybe a 1 here because the input tape is, the pointer is initially at the first position. Remember, x is not built into the configuration. X is considered fixed. So that's some configuration. And then a deterministic Turing machine would just go to a next configuration. But there's 2 different configurations that the non-deterministic one can go to. So some configuration here, some configuration here. And in some sense, the process of the computation is like a binary tree. But it is possible that one configuration will lead to a configuration that we've already drawn. So in this graph, you just draw all possible configurations. There's polynomially many of them. And you put the edges in according to the 2 possible transitions out of each state. OK, except for the halting configurations. Some configurations are halting when you get to either QAccept or QReject. They have no outgoing edges. Questions so far? You remember this somewhat? OK, another thing we did last time, which is nice, is we observed that without loss of generality, we can assume there's just a unique accepting configuration. OK, so I mean, if we didn't do anything out of the ordinary, then given n, it could accept in any number of different configurations. But it's not very hard to adjust n so that just before it's about to accept, it erases, it cleans up its entire work tape, and it moves all 2 of the tape heads back to the beginning, and then accepts. And it's easy to adjust n to do that in such a way so that it doesn't change what language is accepted or the fact that the space complexity is order log n. So we can assume there's a unique accepting configuration called Caccept that looks exactly like this. You end in the accepting state with a blank tape, and the input tape head is back at position 1. Let's say this is here. Oops. It's got, I don't know, it could have more than one arrow coming into it. OK, and finally, remember, what does it mean for non-deterministic computation to overall accept? I mean, the key point is that if you have such a machine n and you have such an input x, then n of x sort of overall accept if and only if there's a path in this configuration graph from C start to C accept within this graph. OK, so I haven't actually quite yet gotten into the proof per se, in the sense that so far this is all like a theoretical exercise. I'm just saying, if you have this machine n and an input x, then this graph exists. And if you knew about this graph, you could decide whether n accepts x by checking if there's a path from one state to another in it. OK? OK, so of course we want to use this fact to prove these theorems. So the easier one is that NL is in P. So let's prove that. So yeah, how are we going to prove this? Well, can somebody say? Or say the idea? I mean, some of the idea is sort of already up there, but there's a few more things to say. Yeah? Yeah?
Let there be a consider an arbitrary language like this, then we can represent its solution as, or its computation path as this graph that therefore we can get to if all numbers are occupied, but it takes all the time to start to the exam.
Yeah, I mean, the idea is, I mean, as you say, you can just, in polynomial time, OK, so let's say let the A be in NL, be decided by non-deterministic machine n with space complexity log n. OK, now we know for any x, this graph exists, and it's of subpolynomial size. You know, has at most polynomial in n vertices given x. So, you know, we need to define a polynomial time algorithm that decides A. So here's a polytime algorithm for deciding whether x is in A. Well, we simply build this graph in polynomial time. We literally write it down. I mean, it's not just that this graph exists, but it's not like, you know, it just hypothetically exists, but it's maybe hard to find. I mean, it's like you can explicitly, the algorithm can explicitly create it without too much trouble. And one thing to know here is the algorithm can, you know, this algorithm that's solving A, it can like know n. OK, so n here is just some non-deterministic machine. So it's like some source code for a Turing machine that has maybe some goto boths in it, or that has two transition functions, delta 0 and delta 1. It's like fixed, and you know, A can be assumed to know that. So it can be like built into the definition of A. OK, the only thing that's not known is x. That's the thing that's varying. So x comes in. So what is the algorithm going to do? Well, the main step is going to, let me call this m. So it's going to, first step, like literally explicitly write down, you know, construct and write down this graph. OK, and for example, I mean, let me expand on how it'll do that. So for example, the first thing it'll do is maybe write down all the vertices. Just make a list of them. So in more detail here. OK, you can also assume, you know, that if n runs in space order log n, that, you know, the algorithm knows a constant c such that it runs in space at most c log n. So it knows that there are, and you know, it knows the size of the alphabet and so forth. So the algorithm knows some big number k such that the number of configurations is at most capital K. So in fact, does the algorithm need to know x in order to do this step? Yes? I think no, right? I mean, so the configurations just look like this. So it just writes down like all possible strings of length, you know, little c log n, all possible ways of like sticking a state symbol in, all possible numbers between 1 and n here. OK, and there's, you know, it's like some little text generation process. But there's basically only like, at most, poly n of these. And the algorithm can just write them all down. Actually, the names of the vertices don't depend on x. What the edges are, like what arrows go where, do depend on x, right? Because, for example, let's say you're in some configuration that looks like Q, maybe, I don't know, A, Q2, B, B, semicolon 3. And you want to know, the algorithm wants to know, OK, like what two configurations does this configuration go to? Well, it sort of has to look at the source code of capital N and say, all right, so capital N, when it's in state Q2, what does it do? Well, what it does depends on three things, really. I mean, what letter it's reading on the work tape, which in this case is B. So I can look at the source code for n and be like, OK, it's reading B. And then it also depends what letter of x it's reading on the input tape. So it's the third letter of x. So now the algorithm M that we're constructing actually has to know x and like look to see what is the third letter of x. And so now it knows what the Turing machine n would be reading on the work tape and also on the input tape. And then also it has, like two different source code instructions. Like a go to both. It can go to this configuration or that configuration, each of which is like either move right or move left, and increment this or leave it the same or decrement this, and maybe write a different symbol. So like, by studying the source code, it'll go to a configuration that's probably like A. Maybe this will change to another letter A, Q4, B, and then maybe this will be incremented. That's like one possibility. Or like maybe the other non-deterministic thing it could do is go left, and then maybe it's Q5. And then maybe it, I don't know, doesn't change this, so A, B, B, and maybe it moves this one down, so 2. So there's two possibilities at every configuration for where it goes. But M can figure out these two configurations that you go to from here by studying the source code of capital N, which is just some fixed source code that's fixed for all time. And it also needs to know x, because it needs to know what symbol is being read on the input tape, which you can figure out by looking up in the third position. Does that make sense? Yeah?
Going back to like writing all the vertices.
Yeah.
You said we didn't need to know x for that step.
I thought so, yeah.
But don't we need to know n?
Yeah, you definitely need to know n. Yeah, because you need to know like what is. You don't even need to know that much about n. You don't really need to know what its transitions are or anything. You just need to know like what is its tape alphabet.
I was talking about little n.
Oh, little n. Yeah. OK. Yeah. Yeah. You need to know little n, which depends on x. That's right. So really, the first line should be determine n. So given x, like compute n. That's true. Good point. OK, so write all the vertices of V. And then explicitly, just write down. You can imagine that's like making the adjacency matrix of the graph. Explicitly write all edges E. And this takes polynomial in n time. And you need to know x for this part. And just another observation here. I mean, another way to do it is even a dumber way. But like instead of going through each configuration that you wrote down and calculating the two outgoing configurations, you could also just write down all pairs of configurations. That's still polynomially many pairs. And then just like ask yourself, is it true that the Turing machine can transition from this one to that one? So in other words, basically, you have to be able to figure out for yourself for all pairs of configurations, C and C prime, whether or not it should be in edge. But this is, I just sort of described it in words up here. This is some sort of very simple textual check. It's certainly in polynomial time. Even better, spoiler alert, it's going to be in log space. OK, so I'm just trying to argue here that it can literally write down the whole graph. OK, and then the final thing it needs to do in order to decide whether n of x accepts is based on this star. It can just, let's say, use breadth first search to check star. OK, that's a poly-sized graph. It's explicitly written down, so it comes to the answer of whether or not n of x would accept. OK, and it does the same thing, and therefore m of x decides correctly if x is an A, and so m decides the language A. Any questions about that? OK, so actually, let me just write it even slightly more explicitly. This is kind of important. It now just solves this stpath problem on the input g, which depends on n and x, which it now is explicitly written down, c start, that's the starting vertex name, and c accept. OK, and path is in polynomial time, so I can do that. All right, so now I want to show this also in log space log squared n. And the proof is pretty much the same, almost, except we're going to use Savage's algorithm here instead of breadth first search. Well, there's a little bit that we need to check. So of course, the idea is that, OK, let A be decided by log space machine n and space log n. OK, we want to come up with a log squared n space algorithm. So for deciding if a string x is in A, the first step is also going to be compute n. We talked about that last time. You can do that in log n space. But this you're not going to do. You will not explicitly construct and write down g, because you don't have space for that. I mean, you have log squared n space, but you have polynomial in n many vertices. So that's too much for you. But we still want to, do this. So this is, we're not going to do this explicitly. But we still do want to do this using Savage's algorithm. OK, so we still want to use Savage's algorithm to decide this. And that's a log squared n space algorithm, as we saw. But it assumed that the input graph and also, I guess, the start and final vertex were written on a read-only input tape. Right? That's the model that Savage was working in. And that's not what we have here. We don't have the graph g and x like written on a read-only input tape for m. Actually, m just has x written on a read-only input tape. But we'll be OK. OK, so the only difficulty here, as I said, is that, m has, x on its read-only input tape. And we sort of wish it had, this g n of x. OK, because if it did, then we could just run Savage's algorithm. I suppose, the Savage's algorithm, the path algorithm also has c start and c accept that it has to think of as part of the input. But those are both length order log n. So it doesn't matter if they're written on a work tape or a read-only input tape. That's fine. But it's OK. So I mean, the point is you just don't need to write, it doesn't need it written explicitly. If you think about how the algorithm works, or you vaguely remember how it works, what does it do? I mean, one thing it does is it enumerates through all vertices. It's recursive. Has log n depth of recursion. And in one recursive step, it is log space. And it's trying to decide if you can get from x to y in a certain number of steps. And it enumerates all the midpoints, potential midpoints. And then recursively checks if there's a path from S to the midpoint and the midpoint to T. So, you can enumerate all vertices in V. I shouldn't say U, I should say M of X. In log n space. That's fine. We just need to be able to check that the machine can, M that we're constructing, can just write down, reusing space, the succession of all the vertices. And that's not too hard, right? I mean, it can write them down in alphabetical order or something. And it only needs to write down order log n bits to record each configuration. And you can have a systematic process that just enumerates all of them. So that's all fine. And then actually, we talked about this a little last time. When does Savage actually even read the input? When do you even look at the input in Savage's algorithm? It's in the base case of the recursion, right? The very base case of the recursion is when you're checking if there's a path from x to y in less than or equal to 1 steps. First, you check if x equals y. That's fine. But finally, you also have to check whether x, y is an edge. So really, Savage only needs that, just need that m given two configurations, C and C prime, can check. At every stage, we want to make sure we use at most log n space because there's a recursion of depth log n. Can check in order log n space if that's an edge. We talked about this when I said, does it matter if Savage gets its input in adjacency list or adjacency matrix format? It didn't really matter, as long as you can, in log space, check if a candidate edge is a real edge. And we talked about exactly this process here. And it's not too hard. If you have two configurations written out, your m, you're trying to know if n could transition from C to C prime. If it does, well, as you said, we have to study the source code of n. You have to look up what x's value is in this position. But this is something we also talked about last time. If this is some log n bit number, if you want to retrieve from the true input tape, which stores x, the third character of x, or any character of x, you can do that in log n space. And otherwise, you have to just check that these two work tapes look the same modulo some little transformation that n does. OK, so you actually hardly need any space. The only space you really need is maybe a little counter to go look up the third value of x. OK, so let me not really write much more, but check. I'll just put a check mark here. You can do that. OK, and let me say that completes the proof of the theorem, that NL is in space log squared n. Any questions about this? OK. Great. So let me just make a couple incidental observations when we're here. This whole story, actually, let me not erase this yet. This whole story was about NL. That NL is contained in polynomial time, and NL is contained in log squared n space. But there was nothing overly special about L here, log space. In fact, L was basically the least amount of space such that all of this was sensible. So you can basically not really do anything properly in less than log space. But you can run this exact same proof for an amount of space that's bigger than log n. And what will happen? So let's consider n space f of n at least log n. So practically everything is the same except for basically one thing. This log n would become f of n. And this would just become exponential in f of n. So the whole story would be exactly the same except this graph, this configuration graph of your non-deterministic fn space-bounded machine would have 2 to the order f of n vertices. So your polynomial time algorithm for checking for the existence of a path would run in polynomial in this amount of time. Polynomial in this just puts another constant factor in the exponent. So what we can conclude is that n space f of n is contained in deterministic time 2 to the order f of n. OK, and if you think about Savage's algorithm, it basically actually runs in space which is the square of the log of the number of vertices. Because the recursion depth is like log of the number of vertices. And the amount of space used at each step is about the amount of space you need to write down the name of a vertex, which is also about log the number of vertices. So I'm writing this theorem strangely, but it's n space f of n is contained in time 2 to the order f of n. And also, it's contained in space f of n squared, deterministic space. It's really 99.9% the same proof. Any questions about this? OK, in the interest of like 100% full disclosure, it's super boring. But if you really want to prove this theorem literally for every function f of n, which is at least log n, you have to think about whether or not you need to worry about f of n being space constructible. Because like, you know, when you're writing down all the vertices, you need to know like how many vertices to write down, like how much space the machine is hypothetically using. It's supposed to, when f of n was log n, you just were like, well, it's log n, so I can just know that. But f of n could be some super bizarre function. So it's very easy to prove this when f of n is like a normal function, which is space constructible. And we usually only care about it in these cases, like when f of n is poly n or log n. It's also not hard to prove it even when f of n is not assumed to be space constructible. You just need like a little bit of trick that says you can just do these algorithms anyway, even if you're not exactly sure what f of n is. It's not worth our time to even worry about that. But actually, Sipser takes note of this. If you want to look at Sipser's proof of these theorems, he actually has like a paragraph where he comments about how you don't even need f of n to be space constructible to prove this theorem. But I really don't care because we basically only care about this algorithm when f of n is a normal function anyway. Yeah?
What's an example of a computable space / time not constructible, but like something that's bad?
A non-space constructible function?
Yeah.
It's just like our same like things for like a non-time constructible function. Like, you know, you could take like function f of n, where f of n is like one value if the nth Turing machine in like you know, alphabetical order halts when run on an empty tape, and it's like some other value if it loops forever when run on an empty tape.
But that's not computable though, right?
Yeah. You can also make it worse. You know, you can say instead of whether it halts or not, you can say whether it solves some extremely difficult problem, which is known to not be in a small amount of space by the space hierarchy theorem or something. So it's really only like literally insane functions f of n where this comes up. OK, so good. So actually, let me just, I mean, as I said, we pretty much only care about this fact for like normal-ish functions like log n, or the second most popular one would be a polynomial. So in fact, like, if you take f of n to be n to the k for some fixed value k, what do you get? You get non-deterministic space n to the k is contained in time exponential in n to the k. And it's also contained in space n to the 2k. And now if you take the union of these statements over all k, then what do you get? This becomes what you might call non-deterministic polynomial space. So anything that can be solved with an amount of space that's polynomial by a non-deterministic machine. And then this becomes, well, actually, this one's a bit less interesting, but this is exponential time. But this just becomes p space. OK, so you can ignore this one because it's less interesting than this. This says that non-deterministic polynomial space is contained in deterministic polynomial space. So these classes are actually equal because deterministic space is contained in non-deterministic space. So p space equals np space. So actually, this is kind of like p, in a way, it's like p equals np for space. That's kind of amazing. You know, and that's actually an illustration of what I was saying when we started this space complexity discussion, that somehow in the context of space complexity, non-determinism doesn't seem to be too powerful. this basically says that like you can get rid of non-determinism by squaring the amount of space you use. So in particular, NP space is just the same as P space. So this is why you'll never see like the letters NP space written down in a textbook except like more than one time when they make this observation, because it's just the same as P space. Let me also comment while I have it up on the board. One of the very first things we showed about space at all was that space, well, I guess it's here. It was that space, deterministic space after the n, is contained in time exponential in f of n. That's the most basic relationship between space and time. And now we just observe that literally the exact same thing is true even for non-deterministic space. OK. So good. So one way you could sort of summarize a little bit in words what we did here in proving these theorems is, as I said at the beginning of class, like we basically saw that non-deterministic space-bound computation, in particular non-deterministic log space computation, was it basically exactly boiled down to the ST path problem. I mean, understanding what a non-deterministic log space machine will do on a given input x is exactly the same, basically, as determining if there's a path in a certain graph where the graph bore an easy relationship with the machine. So in fact, a theorem that we will eventually prove is exactly this. The ST path problem is complete for NL. It's NL complete. But I'll have to put this in quotation marks because, well, we haven't defined it yet. We know what NP complete means. But it's not even the case that if you just take the definition of NP complete and change NP to NL, that you'll get what NL complete means. So we have to dive in a little bit for the next while into understanding what we should mean by this. But this is actually our motivating goal, is to set the definitions up so that this is like a sensible and good statement. OK, so what is going to be the definition of this? Well, NP complete means, there's two things. One, it should be that, OK. So I'll start writing the true definition. A language B is NL complete if two things happen. One, B is in NL. That's just like in NP completeness. And this is true for the case of path, right? We saw before, this is the first thing we talked about when we introduced NL. It is indeed in NL. So that's not the tricky part. The tricky part is that we want to capture the idea that not only is it in NL, it's sort of the hardest problem in NL, in the sense that any problem in NL can be reduced to it. OK, it's like sort of no harder than it. So we want for all A that are in NL, A reduces to B. But this is where we still have to start thinking. What do we mean by reduces to? OK, so in the definition of NP complete, we had M and P here. We had polynomial time mapping reduction. But that's a bad choice for this definition. So we could just use our favorite notion of reduce. But this is a bad choice. You could make this definition, but it would just not be a good and useful definition. So why? Why is it a bad choice? What would be a good choice? Why do we even make these definitions in the first place? NL complete or NP complete? We're trying to capture what it means for this to be like the hardest problem in NL, or the problem in NL which is least likely to be in L or some other smaller class. Okay. And so that other one is interesting. We want to say that like it's an interesting question whether NL equals L. Can you get this log squared n in Savage's theorem down to log n? Can non-determinism just be completely eliminated from log space computation? And so you'd like to identify maybe the hardest problem in NL such that if this were in L, then every NL problem would be in L. Right? Just like if 3 sat is in P, then every NP problem is in P. And so what you want out of this notion of reduction, and then the whole point of these definitions, is you want that a theorem that says, like, if A is in, hold on, yeah, NL, and A reduces to B, and B is in NL. Sorry, B is in L. OK, this is not that necessary. But you want that if A reduces to B and B is in L, then A is in L. OK, so we want this to be like a true statement. Because if this were for whatever notion of reduction that we're going to put here, because if this were a true statement, then we would be able to say, assuming, let's say, path indeed turns out to have this property, that as soon as you put, let's say, path in L, then you get that everything in L is in L. Okay? I didn't explain that perfectly. So, I mean, any question? All right, this is exactly what we had for, let's say, P, right, with our notion of polynomial time mapping reduction. That if A reduces to B and B is in P, then you want that A is in P. So that you could say, for example, if you know that everything in NP reduces to 3-sat, and then if it turns out that 3-sat is in P, then everything in NP is in P. But, you can ask, is this true for our usual notion of reduction less than or equal to MP, polynomial time mapping reductions? So you say, suppose I have a polynomial time mapping reduction from A to B, and then it turns out that B I show is in L. Can I conclude that A is in L? It's a bit like the homework problem, but it's going to go wrong, right? Because, how do you try to show that A is in L based on these two facts? You say, OK, given a string x, I want to decide if it's in A in log space. What will I do? First, I'll run the reduction, get an instance of B, and then use my log space algorithm for B. But if your reduction is a polynomial time reduction, then you're kind of dead, right? I mean, you take x, you run a polynomial time reduction, you're already outside the class L. So, you kind of see what you need in order to make this work is some kind of notion of a log space reduction, so that this first step of doing the reduction doesn't take you outside of log space. OK, so this is like a key idea in life, or at least in complexity theory, that just, when using reductions, your notion of reduction, I mean, the complexity of your reductions, they must be as weak. The complexity of reduction should be as weak as the weakest class you care about. Let me try to explain what I mean. When you're studying P and NP and polynomial space, what you're really trying to understand is like which problems could potentially be in P. OK, so then it's OK to use polynomial time reductions in studying that. But now if we're caring about like L and NL and log squared N space and P, we're roughly speaking like which problems could be put in really low space classes like L. We really need to use a notion of reduction that's as weak as possible, and it should be no stronger than L. OK, so this is all motivation for why we need to invent a new kind of reduction. It's going to be the same notion of a mapping reduction. X is in A if and only if R of x is in B. But we're just going to change the complexity that R is required to be in. Okay, rather than just saying it's supposed to be a polynomial time algorithm, we're going to have to somehow say it's a log space algorithm. And even that requires a little bit of trickiness in how to define things. OK, so we need to define, well, this symbol, less than or equal to ML. OK, the M stands for mapping. It still refers to the fact that it's just this property where you take a string, you output a new string. You take x, you output some R of x, and x should be in A if and only if R of x is in B. This is called log space reduction. Of course, the L stands for log space. And let's say some things that we want about it. What do we want? We want two things, really. We want some closure properties, which are like these things up here. So we want that like if A reduces in log space to B, whatever that means, and B is in L, then that should imply that A is in L. It would also be pleasant, so this is saying like L is closed under log space reductions, if you want to use a mathematical turn of phrase. And it'll also actually be nice to have the same thing for NL. Right, we have this for P and NP, right? This is our main thing we remembered about polynomial time reductions was if you have this and B is in P, then A is also in P. But it's also sometimes good to remember that we also had it for NP, that if B is in NP, then A is in NP. Not crucially used that this was a mapping reduction. So that's one thing we want. And another thing we want, which was somehow like didn't seem like a big deal for polynomial time reductions, although we used it, it's a little bit trickier in log space, but we should definitely look into it, is transitivity. I mean, if you invent a symbol that looks like then less than or equal to, you better have this, or otherwise your notation is terrible. We want that if A reduces to B and B reduces to C, then that should imply that A reduces to C. This is something that you want because, you know, eventually we start stringing together these reductions to make chains, and we want that to work. OK, so these are two things we want out of our definition of log space reductions. And well, now I'll give you the definition, and then we'll show that they have these properties, and then we'll show that NL is, sorry, that the path problem is complete for NL, and then we'll be done for the day. So here it is. A reduces in log space to B if, well, actually, I'll just write the same definition as we do for polynomial time reductions, but I'll continue to evade the issue. If there exists a reduction function mapping strings to strings, computable in order log n space, and what exactly this means I have to talk about, but let me just finish the definition. It's the same definition, such that for all x, x is in A if and only if Rx is in B. Okay, so this is exactly the same definition as polynomial time reductions, except the reduction has to be computable in log space rather than polynomial time. But finally, OK, now we're going to finish the definition. What does this mean, computable in log n space? So even to talk about, you know, deciding a language in log n space, we had to think about a little. We had to decide that what we wanted was that the input was on a read-only tape for which you're not charged the space. And you're only charged for, you know, workspace. So that could be less than the input size. But now reductions have to map strings to strings. And usually, actually, R of x is usually at least as long as x. That's typical in any reduction. So now, if this has length n, this might have length at least n, but we got to compute it in log n space. So you see, in order to make this, you know, potentially work and be cool, we have to somehow not charge for the output either. Okay, so we need to somehow set up a situation where, you know, in log n space, you can still output something that's length n or bigger. So you might say, OK, let's have a write-only tape where the Turing machine can write down its answer, and we won't charge for the space on that either. Turns out that that's even not the right definition. It turns out that the right thing to have is something even stricter, have a write once output tape. OK, so that this is a tape where the Turing machine writes the answer, but like on this write once tape, it cannot even like go back and change things. It cannot even go back and look at what it's previously written. It can only just like write to it like one time, like a, remember there used to be this thing called a CD-ROM that somehow you could write to one time? I guess like that. I mean, you can only write there. I guess you could even go back and read what you wrote. You can't even do that here. OK, so for the definition of what this means, computable in log space, basically the idea is you'll have like a write once output tape for which you're not charged space. I don't know if that's grammatical, but anyway, for which space is not charged. Actually, there's two ways to define it. This is one way to define it. Another way, maybe I'll put it on a homework or something, is like, OK, let me not get into it. Another way is you could say that like computable in log n space is like if somebody gives you the position of an output bit as part of the inputs, and you're required to output that character, like that character of the output in log space. So there, like you're only required to output one bit. It's a little bit funny because you get like as input the position of the output you're supposed to write. But I think this is going to be simpler. OK, so let me actually draw a picture. So this is, I'm sort of defining here the model for space-bounded computation with output. OK, so for a while we talked about how you even need a bit of a special model for space-bounded computation at all, even when you're just trying to accept or reject. Now we need like an extra twist if you want to allow output. So here you have a Turing machine M. There's this read-only input tape. OK, and here the head could go left, right, stay put, but you cannot write to it. So it has one head on this tape. And you have, let's say, one or constantly many is also fine, space counting, bounded, read, write, work tapes. OK, and finally you have this output tape, which is write once. OK, and what does that mean? It just means that you have an instruction to write onto this cell, and you have an instruction to move the head right one square, or stay put. You can't go back. Let me make one more observation. Let's say that this is hypothetically log n space. That's the case we care about most. I just want to observe that a machine that acts like this, it has input and output, it will still run in polynomial time. Okay, so remember, when we didn't have this output tape or anything, we argued that if you have space-bound of f of n, then you run in time at most exponential in f of n. In fact, in the first half of the class, we proved the same thing with n space. The same proof is true for when you have a write once output tape, because if you think about it, I mean, the presence of what's happening on this tape does not affect the future computation. I mean, what configuration the machine is in, it does influence what symbols it writes to the output tape, but it doesn't affect what will happen next on the main portion of the tape. So everything that we argued about space versus time is still true for these guys. So in particular, if they're non-looping machines, if they run in log n space, they'll run in at most polynomial time, which also implies that they'll never write more than polynomially many symbols. Okay, so one thing to bear in mind is any log n space computation, R, will map strings of length n to strings of length at most poly n. OK. Any questions about this? Yeah.
So we sort of get away with this log n space by doing the write once output tape, but if we generalize it to try to prove closure, won't that still have issues? Because you can't just say there's an exception for write only.
Yep. So yeah, these will take proof. So I'll prove these today, ideally, but I won't prove them next. I'll state that these two theorems are true about this notion, and I'll prove that. But first, I'm going to prove the NL completeness thing, assuming these two facts. Or just, we'll take these for granted. But you're right, they require a proof. And actually, the proof is similar, somewhat similar, to problem 3B or A on the homework about VNL being contained in NL. It's sort of similar. Yeah. OK, any questions? OK, so as I said, the last thing I'll do will be prove these two things about this definition of log space reduction. But first, let me prove this thing, that Cpap is NL complete. This I really, it's an important theorem because, as I said in complexity theory, right, they're always defining like these complexity classes. Let's go to log space with non-determinism or whatever, and it might seem getting a little obscure, but complexity class is a good one to have around, or it's worth study if there's a natural problem that's complete for that class. And Cpap is like incredibly natural, so that means that NL is an incredibly natural class. OK, so let's prove this theorem. Cpap is NL complete. It's basically just the rehash of what we did in the first half of the lecture. So of course, we have to prove two things. But one of them we proved a while ago, which is that Cpap is in NL. OK, that's because the non-deterministic log space algorithm, the one-sentence summary is it can guess a path from S to T and reuse the space and check that that path really exists. OK, the main thing we have to prove is this, that if A is in NL, then A reduces to Cpap. So we'll say let A be any language in NL. OK, we need to show that A reduces in log space to Cpap. And in words, it's sort of like saying that to decide whether a string is in A, you can set up an Cpap problem that gives you the answer. And that's sort of exactly what we did in the first half of the class. I mean, we saw how by setting up this configuration graph, you can reduce the question of whether a non-deterministic machine accepts a string to an Cpap computation. OK, so I'll just say n is an order log n space non-deterministic machine deciding A. So the claim, this is the key claim, is that there exists a deterministic, this is not important, but let me just emphasize it so that we don't forget, log space computable R I guess order log n space computable R mapping strings to strings right, that given a string x of length n, outputs the configuration graph G and x that we talked about before. And also, this is much less important, but and also C start and C accept. All right, so this is the main claim, and the claim completes the proof. Because as we saw before, x is in A if and only if, by definition, n of x accepts if and only if there exists a path from C start to C accept in G and X if and only if R of X is in ST path. Okay, so it really is a reduction. X is in A if and only if the output of R is in ST path. Right, this is what we saw in the first half of class. So we just have to justify the claim. Is that OK? OK, so we talked a couple of times about, after we set up the configuration graph, when we were proving NL is contained in P, and NL is contained in log squared n space, we kind of had to think about the complexity of figuring out the graph given X, with n being fixed. And now we have to dive into that even a little bit more, because we have to figure out the complexity of sort of outputting the graph in this funny write once way given X. But it's really not too bad. So R will output the graph. OK, it also has to output C accept and C start, but this is not too much trouble. These are of order log n space themselves, so it can just save some part of its source code for writing those down at the end of everything. So the main part is how to output the graph. It's going to output it in kind of like an adjacency list format. And it just has to sort of do it. So the only thing we have to remember here is that we can output it. It's OK for us to output the whole graph explicitly. We just have to do it in a write once fashion. This requires a little thought to make sure it's OK. So what do? You just enumerate through all the configurations. OK, and this it can do with the assistance of log n work tape space. You can think of the graph format as saying, here's a vertex. Here are all the vertices it's adjacent to. Here's another vertex. Here are all the vertices it's adjacent to, and so forth. So it'll go through all these and write them irrevocably to the write once tape. So it can write C to the output. Okay, by copying it from a work tape where it has C written. You can copy from a work tape to the output tape in a write once fashion. OK, and then on work tapes, it'll enumerate through all other configurations in the same order, let's say, all configurations C prime. This is also using the assistance of log n work tape space. So you can imagine that it has C and C prime written on work tapes. And now it's going to check if C prime is really an edge in the graph. And we talked about in the proof how that's a log space check. OK, and then if it just decides on its work tape that C prime really is connected to C, then it can just write C prime on the output tape. OK, and then, as I said, then finally it writes C start and C accept. OK, so that's basically it. There's, it's just worth thinking it through. There's nothing overly special about it. And maybe technically you'd have to explain a little bit about how to put some punctuation or something between the elements in the adjacency list. But hopefully we're all kind of past worrying about that too much. Well, you just have to check for yourself that it really, as it's writing out the graph G, it doesn't need to remember what it's already written and so forth. OK, it just can write it out in some sort of straightforward fashion. OK, any questions about this? OK, so this proves that the ST path problem is NL complete. So every problem in NL reduces in log space to ST path. So now, once we prove these things, which we want to have true, then we'll learn that if you could solve ST path in log space, we know you can solve it in log squared n space, but if you could solve it in log space, then you could solve everything in NL in log space. Or even if you could solve it in space log n to the 1.9, then you could solve everything in NL in space log n to the 1.9. OK, so this is all a bit technical, but I got to do technical things sometimes. So last thing I want to do is prove these facts. And basically, you can prove these two facts simultaneously by one more general fact, which is also nice to know. And that's this theorem. If P and also Q are functions computable in log space, then so is their composition. Gotta go to the bad chalk. Can't take it. OK, so this is a fact that we had for polynomial time, and we used it a few times. And I idly kind of commented that, OK, P and Q are computable in polynomial time. Then first you run P on X, and you get its output. And you have to remark that the length of this output is at most polynomially longer than the length of X. So Q runs in polynomial time in the length of this, but that's still overall polynomial time in the length of X. So R of X you can also do in polynomial time. OK, we have to do the same thing for log space, but it's trickier a little bit because, as mentioned, like you cannot just OK, P of X is computed in like this fashion. So the output goes to a read-only a write-once output tape, and you can't just like keep that tape around and then plug in the answer for Q and then do Q. So you have to think a little bit harder. But we'll prove this theorem in a second. But let's see why it implies those corollaries. Now, I won't even really write anything. But one corollary is it's written up there. If M reduces to A reduces to B, and B reduces to C, then A reduces all in log space to C. And well, I think the proof of this, given this, is clear. This means there's some reduction P, computable in log space from A to B. And there's a reduction Q, computable in log space from B to C. And if you put those two reductions together, you get a reduction from A to C. And it's computable in log space if A and B are. And you also get the other fact that if A is reducible to B in log space, and B is in L, then A is in L. How do we get this? Well, again, let's say P is the reduction function here that takes A to B. And now you can basically just let Q be the function which is like the function version of this decision problem. So Q of X equals like 1 if X is in L and 0 if X is not in L. And if B is decidable in log space, then Q is computable in log space, right? Because you just decide whether X is in B or not. But instead of accepting or rejecting, instead you write 1 or 0 on your output tape. basically the same thing. And now if we put these two things together, we'll get like an algorithm R, which on input x, converts it to a problem for B, which has the same answer. And then Q can, on its output tape, write 1 or 0 for whether the answer is, for the reduced thing, is true or false. Well, you're really not supposed to write 1 or 0 on a special output tape to decide, for this definition of A being an L, you're supposed to accept or reject, but you just do the reverse. Like if you're about to write 1 on your fictional output tape, then accept. And if you're about to write 0 on your fictional output tape, then reject. Maybe that was, just think about it if you didn't like those sentences I said in words. I tried to just combine both these two facts into one theorem. And maybe it's basically, again, equally easy if you just think about it, but I'll call it an exercise. The same thing for NL. So if A reduces to B, and B is in NL, then A is in NL. OK, and I'll leave that to you. But you can take it for granted in subsequent times. OK, so the last thing I need to prove to complete everything is this theorem about how if you have P and Q computable in log space, then their composition is computable in log space. OK, so let me do the proof. Let me call it like a sketch, because maybe there's a few like low-level Turing machine details I'll kind of skip. But let's say that, you'll get the idea, say that P runs in time n to the P, and Q runs in time. I actually think this is important, but Q runs in time n to the Q. Okay, remember we saw that polynomial, I said that log space machines run in polynomial time. And we really just need this as like a bound on the output length of P and a bound on the output length of Q. Okay, and really maybe it should be a constant times n to the P, but let me ignore that. OK, so we're trying to design a machine M that takes as input x, well, M takes as input x. And let me always write n for the length of x. And it's trying to compute R of x, okay, which is it's trying to compute Q of P of x. So let me also, just for notation, let y be P of x. Okay, so the length of y is at most n to the little p. Okay, so as M is supposed to try to compute Q of y. In particular, it's going to need to know y in order to try to do that. But let's remember like what the actual setup is for M. Right? The actual setup is for M, it's got x written on a read only input tape. OK, and down here it's got a write once output tape. And it has to try to get R of y on here. OK, and it has some work tapes. These work tapes are supposed to have a log n space among them. OK, and it has heads on all of these things. OK, and it has to do this. So, as I mentioned, you cannot just have M simulate P on x to get y, and then go from there. Because if you run P on x, you need to imagine that you have a write once output tape, which you do have, but you better not write P of x onto it, because it's write once, and you've got to get R of y onto there. Sorry, this should just say Q of y. Sorry about that, which is R of x. And you can't just say, OK, well, I'm going to use work tape to store p of x, because p of x could be very long. I mean, y can be very long. It could have length n to the p, which is polynomial length, not just log n length. But it's OK. So M will just try to simulate Q. So I'll add here try to. And it'll pretend it has a read-only input tape for y. OK, so M will actually sort of start by like trying to do Q. And it'll pretend that it has a read-only input tape for y, which looks suspicious at first, because like it actually has a read-only tape for x, and it doesn't have y anywhere. But if it can manage to carry out this pretend, then it'll be in good shape, because it'll finally act by writing Q of y onto the output tape, which it's supposed to do. OK, so the only thing we have to worry about is how it can simulate having read-only input access to y, which is p of x. So, it can't just write y down. So actually, it'll do this by M will keep track of sort of Q's input tape head location on a work tape. OK, and this input tape head location is going to be log of the length of y, which is like n to the p, which is order log n bits. So that's fine. In this sort of simulation of Q, M doesn't really have y on a read-only input tape, but it'll keep track of where Q thinks the input head is, just as a position on some work tape. So basically, M needs to be able to like get, if you will, y, the ith character of y. If I call this tape head location I. Because it's trying to simulate Q. Q will be like, now I will look at my input tape to see what character is written there in the ith position of y. OK, and M needs to be able to fulfill that. Okay, but it doesn't even have y. So how will it do that? For each step of Q. Somebody want to say? Yeah?
Sort of an on-demand thing. If it needs the next character, you compute until you write. You're supposed to write for that, write only for the next character, and just use that instead of writing.
That's right. So the solution is extremely, extremely time inefficient. If you care about time complexity, you're like, this is ridiculous. But if you care only about space complexity, it's fine. So what you do is, every single step of Q, you need to know yi. You run the whole computation of p of x. Well, most of it. Not quite. So when you run p of x, to run p of x, you need a read-only input access to x, which you have in the overall setup. And you supposedly have this write once output tape that you're writing onto, but you don't actually do it. You don't actually write on your output tape. You don't even write on the work tape. Just like every time the computation of p of x writes a symbol, you basically throw it into the garbage. But you retain a counter. And you retain a counter until you've written I many symbols, hypothetically. And then you know the answer. And then you can actually stop the computation of p of x if you want. So you just you run the computation of p of x with a fictional output tape. Throwing, you're keeping a counter of how many symbols you've written up to I, throwing the output in the garbage until you get to the ith symbol. OK, so you use the work tape to keep track of how many symbols you output. And once you get to the ith one, you're like, great, I know it. Now I can do one step in the computation of q. And then to do the next step, you're going to run p all over again to get the next yi. OK, that's it. I'll see you on Thursday.